Okay, simple equation, solve it using Laplace transforms. We don't need to solve it using Laplace transforms. It's really easy to solve, in this case, using an integrating factor. But we're going to do this now. We take the Laplace transform of y prime plus 4y plus Laplace transform 2 cosine of 5t, which is going to be the Laplace transform of y prime. Now, I'm using the linearity of the Laplace transform, the Laplace transform being defined in terms of integrals. It's really easy to prove linearity. And then you have inverse transforms, and it's pretty easy to prove linearity there too. So I'm not going to prove those things, I'm just going to use them. So by the linearity, Laplace transform of this plus this is the Laplace transform of this plus the Laplace transform of this. And I've kind of skipped a step. The Laplace transform of 4y is 4 times the Laplace transform of y by the linearity. And it's just because you can pull the 4 out of your integral. I'm going to be a little more careful over here. This is going to be 2 times the Laplace transform of the cosine of 5t. Well, the Laplace transform of yt is negative y of 0, using y as our function instead of f, but that's straightforward, plus 4 times the Laplace transform of y. And I got a step ahead of myself. In other words, there's more to the Laplace transform of y prime. Okay, now looking back at our result, just making the connection between the f and the y. If it's y instead of f, then it's negative y of 0 plus f times the Laplace transform of y. S times the Laplace transform of y. Okay, so this gives you all of this. And then you got 4 times the Laplace transform of y equals 2 times, okay, it's cosine of 5t. Now let's look back at the Laplace transform of the cosine. It's s, the cosine of kt. The Laplace transform of the cosine of kt is s over s squared plus k squared. Okay, so k is 5. So s squared plus k squared is s squared plus 5 squared, which is s squared plus 25. Now what we're trying to do is we want to solve for the Laplace transform of y, which we have here and here. So we can factor out the Laplace transform of y from s plus 4. So this is s plus 4 times the Laplace transform of y. And then we can subtract y of 0 here. So actually, let's give us, we do need an initial condition. The initial condition, let's say, is y of 0 equals 2. Now I'm not going to write that in yet, but I could write a negative 2 here. I'm going to keep it in this form for a minute. Well, I've got the 2 factored out, and there's no reason to keep it factored out now. I can multiply the 2 by the 5 and get 10, obviously. So we have 10 over s squared plus 25 plus y of 0. So now our Laplace transform and I guess I want to put in my y of 0. Okay, so that's no, man, I'm not lining things up well, am I? 10 over 25 plus 2. So L of y then equals 1 over s plus 4 times 10 over s squared plus 25 plus 2. Well, we can use a common denominator here. We're going to get 2 times the quantity s squared plus 25 over s squared plus 25, which is going to give us a 2s squared plus 50 in the numerator. And then that's divided by s plus 4 times s squared plus 25. Okay. What we need to do next to solve this for y is we want to do what's called an inverse transformation on this. In other words, we want to find the function whose Laplace transform is s squared plus 50 over s plus 4 times s squared plus 25. Now that's going to take a little bit of algebra. And the algebra is really the toughest part of this process, assuming you have reasonable functions. So we're going to say that L of y, no we're not. Yeah, we are. Okay. Okay, before I do the inverse transformation, never mind. I thought I knew what I wanted to do. We're going to do that on a separate board in a separate video. I'm just going to say now that y is going to be the inverse transformation of this, and I'm just going to say it here and then we'll work it out next. That would be then we're going to say it and it's going to be a little hard to read. You're going to have partial fraction decomposition of this in terms of the denominator. You're going to have an a over s plus 4 plus bs plus c, and some days it's all bs, but bs plus c divided by s squared plus 25. Now the inverse transform of a over s plus 4, whatever a proves to be, and we'll determine the values of a, b, and c using partial fractions. But the inverse transformation of a over s plus 4, well, it's going to be a times the inverse transform of 1 over s plus 4, And 1 over s plus 4 is just an e to the at with a equal to negative 4. And then we have an s squared plus k squared. What do we have? We have s squared plus 25. We have an s squared plus 25 there, okay? And what are we going to do with that? Okay, well, if it's a constant over s squared plus k squared, it's going to give us a sine of kt. K is equal to 5, so it's no surprise that we're going to get a sine of 5t out of this. We're also going to get a term that's an s over s squared plus 25, and that's a cosine of 5t. Some multiple of the cosine of 5t. So by doing the partial fractions, we can determine what multiple of e to the negative 4t is part of this solution. And of course, you know e to the negative 4t is part of this solution. That's your solution to the homogeneous equation. And then you're going to get a sine and a cosine of 5t, which is exactly what you expect from this form, just thinking of undetermined coefficients. Now, there's no point at all in doing a Laplace transform of this equation because it's much easier to solve using undetermined coefficients. But it illustrates the process and how partial fractions come into play. So we're going to go on and do the partial fractions in this.